Welcome back to the deep dive. Today we are taking a really fascinating turn. We're not just looking at what LLMs do.
No.
We're looking at what they're made of. I mean, deep down at the level of math, even physics.
Hmm.
We've got a set of sources that treat the transformer, the engine, in everything from GPT to, all the modern AIs.
Right.
Not as software, but as a dynamic system.
And our mission today really is to get into the guts of the attention mechanism.
The core of it all.
It's where the magic happens, right? Where the model decides which words or tokens are connected. And we're going to use this really specialized language, the language of dynamical systems, to answer a huge question.
Which is?
Why does this mechanism constantly, and I mean constantly, drive tokens to clump together, to cluster, and what mathematical tricks are engineers using to stop the whole system from just, collapsing into useless mush?
That's the paradox, isn't it? The whole architecture that Vaswani and his team introduced, it relies on self-attention, which is this massive data-dependent free-for-all between every single token pair. It's like a giant room where everyone is shouting and listening to everyone else all at once to figure out who's important.
And because that process repeats layer after layer, sometimes hundreds of times, you can't just think of it as a simple feed-forward network. It's mathematically, it's an iterative composition.
A discrete time dynamical system.
Exactly. And if you take the continuous limit, which makes the math tractable, you can model the whole transformer as nonlinear flow.
Which puts it right in the world of physics with concepts like interacting particle systems.
Yes.
So we're really treating these token vectors, the things that represent our words, we're treating them as if they're physical particles.
We are. And their movement, their change in meaning is governed by the average behavior of the whole sequence, the mean field dynamics.
And the main feature, the biggest outcome of this whole system, is this powerful, inherent drive towards global clustering.
Correct. The system wants tokens with similar meanings to get close. And that's a good thing. You want that.
Sure.
But if that drive goes unchecked, you get what's called representation collapse.
Where the vectors for cat and democracy and car all just merge into one blurry, meaningless point.
And suddenly your billion-dollar model is useless. So yeah, understanding the physics of that collapse is everything, because modern AI engineering is basically a long, sustained effort to manage it.
Okay, so let's dig into that. How do we model this drive toward collapse? I know the full transformer is way too messy for this kind of analysis.
Oh, it's a nightmare. You've got multi-head attention, MLPs, all these normalization layers. It's too much.
So we simplify.
Simplify. We derive these continuous time models, these flows, that capture let's say, the essential physics of what's happening. And we can focus on two core idealized models that track a token's position.
What was the first one?
The first one is called the self-attention dynamics, or just SA.
SA, got it.
And this model has a really important mathematical constraint, an orthogonal projection.
Okay, what does that do in plain English?
It does one crucial thing. It forces every single token to stay on the surface of the unit sphere. It keeps their length constant.
And why is that important?
Because it simulates the effect of post-layer normalization, or post-LN. It's a key piece of the architecture in many of the earlier models.
Okay, so that's the SA model. What's the other one?
The second is the unnormalized self-attention dynamics, or USA, and it's simpler. It just omits that projection.
So the vectors can grow or shrink however they want.
Exactly. And what's so wild about this USA flow is where it comes from mathematically. It is the Wasserstein gradient flow of an interaction energy.
Whoa, okay, that's a mouthful.
It is, but just think of it like this. It directly links the attention mechanism to optimal transport theory.
The math for the most efficient way to move a pile of sand from one place to another.
Precisely. It means the system is always trying to minimize an energy cost.
Yeah.
Every interaction is, in a sense, an optimal move.
That's a very deep connection. That a chatbot is governed by the same principles as, logistics and resource allocation.
It gets even better. If you simplify it down to just 2 dimensions, you constrain the tokens to a circle, like points on a clock.
Yeah.
The USA dynamics become a version of the classical Kuramoto model.
The Kuramoto model.
Yeah.
From physics.
Yeah.
The one used to describe how fireflies start blinking in unison.
Or how metronomes on a shared table will slowly synchronize their beats. Yes, that exact model.
So you're telling me the core mechanism of a transformer is mathematically identical to a system that's designed to find consensus. Total agreement.
I am. The math shows The inherent drive is synchronization. And in vector space, synchronization is just clustering. The tokens are fundamentally driven to align.
And this isn't just a theory, right? People have looked inside actual models and seen this happen.
Oh, absolutely. The evidence is overwhelming. Researchers looked at pre-trained models, and they tracked the similarity scores between tokens across the layers.
How close their vectors are.
Exactly. They plotted histograms of the inner products, where a 1 means perfect alignment, and you see this dramatic shift. As you go deeper, from layer 0 to layer 48, the whole distribution just squeezes itself towards 1.
So the tokens are visibly collapsing into tighter and tighter groups.
They really are. You can see it clear as day.
Okay, but this is where the paradox really hits me.
Mm.
Because the math predicts something much more, well, catastrophic than just clustering.
It does, the global clustering theorem. It's a brutal result.
And it says that for basically any starting configuration, both of these models, the SA and the USA,
They are mathematically guaranteed to converge to a fully synchronized configuration.
meaning they all collapse to a single point.
A single point, a Dirac mass. The distance between any two tokens, any two concepts, goes to 0.
So the only truly stable state for the system is mush, total collapse. And any other state, like having a few distinct clusters, is just a temporary stopping point.
Just an unstable saddle point that the dynamics will eventually escape from.
But wait, hang on. If that theorem is true, then you're telling me that GPT, every time I use it, should just collapse into a single point of mush after, what, 5 layers? How do any of these models actually work?
That is the multi-billion-dollar question. And the answer is metastability.
Metastability.
The system does want to collapse, but the path it takes to get there is incredibly slow and structured. First, tokens collapse very quickly within their local neighborhoods. They form lots of small, tight clusters.
Okay, so they form little clinks.
Right. And then they get stuck. They enter what's called an exponentially long-lived metastable state.
They just hang out in their groups for a very, very long time.
An almost unimaginably long time relative to the network's processing speed. Geometrically, they're sitting in a very, very shallow part of the energy landscape.
So they're stable, but not truly stable. They're in a divot, not at the bottom of the deepest canyon.
Perfect analogy. And when they finally do escape that divot, when two clusters finally merge, it happens incredibly fast. An abrupt, violent change.
A saddle-to-saddle transition.
Exactly. And if you plot the energy of the system over time, you see this pattern.
This is the staircase profile I've seen in the papers.
That's the one. Long, flat plateaus of metastability, and then boom, a sharp drop when two clusters suddenly merge.
And that suddenness comes from the softmax function in the attention, right? There's that sharpness parameter.
The inverse temperature, it controls how decisive the attention is. As you crank up beta, the attention becomes a hard argmax.
Meaning it only pays attention to the single closest token.
Right. And in that situation, the closest pair of tokens interacts and merges exponentially faster than anyone else. So the merger looks instantaneous. It creates those sharp steps.
So by tuning beta, you're not just tuning the speed, you're controlling the whole structure, the number of temporary clicks the system can even form.
You are. There is a mathematical link that shows the number of these metastable states is proportional to the square root of beta. It's an incredible connection between a simple parameter and the expressive capacity of the network.
It's amazing that this isn't just some weird physical effect. It's actually related to, practical AI techniques. I read the SA dynamics are basically a continuous version of the mean shift clustering algorithm.
Yeah, that analogy is so helpful. Mean shift is explicitly designed to find the modes, the peaks of a data distribution.
So the tokens are clustering around the dominant semantic concepts in that layer.
That's the idea.
Okay, let's switch to management. We know the system is desperate to collapse. So how do the architectures we use in the real world control this terrifying drive?
Well, for that, we can use a really simple tool called the equiangular model. We just assume all token pairs have the same correlation. It lets us calculate the speed of collapse exactly.
And the findings are pretty stark, right? With that normalization, it's game over.
Immediately.
Yeah.
Catastrophic.
Yeah.
In the unnormalized model, the USA one, the clustering rate grows exponentially with that sharpness parameter, theta $. You get representation collapse almost instantly.
But the SA dynamics, the one that simulates layer normalization, it's a totally different story.
Totally different. That spherical projection, it acts like a brake. A speed regulator. It keeps the contraction rate constant no matter what beta is. It prevents the exponential runaway.
So that's the basic proof for why we need layer norm.
It's the simplest and clearest demonstration, yes.
But then you have the difference between the two most popular schemes. You have the older post-Ellen and the now dominant pre-LN, which is in GPT and Llama.
And this is where it gets really subtle, but also really important. They both use the same underlying attention math, but they regulate the speed of contraction differently.
Okay.
Post-LN, which is what our SA model represents, it results in an exponential rate of convergence.
The distance between tokens shrinks exponentially fast, which for a 100-layer model sounds awful.
It is. You run out of room, you run out of separation very, very quickly. But the pre-LN scheme, it induces a much, much slower polynomial convergence rate.
So you have polynomial versus exponential.
Exactly.
And that seems, I mean, that's not just a small tweak. That sounds like the breakthrough that makes deep models actually work.
It absolutely is. This is the critical architectural takeaway. The polynomial rate of pre-LN means contraction is so much slower. It lets you actually benefit from having a deep network. The designers figured out how to make the model last longer before it turns into mush.
They're extending the lifespan of that metastable state. They're managing the collapse, not preventing it.
That's the perfect way to put it.
Which brings us to long context. When your sequence length nowhere gets huge.
Right. With long sequences, the attention scores tend to flatten out. And that, ironically, makes things collapse even faster. So to fight that, models use logarithmic attention scaling.
They tie the sharpness parameter, beta-ol, to the logarithm of the sequence length. Why that specific formula?
Because the math demands it. Our model showed this logarithmic scaling creates a definitive phase transition.
A phase transition, you mean like water turning into ice?
Exactly like that. There's a tuning factor, let's call it gamma. If your gamma is too small subcritical, the system boils. It rapidly converges to uniform collapse. Useless. If your gamma is too large supercritical, the system freezes. It becomes rigid, identity-like. It doesn't learn anything.
So the engineers have to tune it just right to keep the model teetering right on that critical edge between boiling and freezing.
They keep it in a critical sparse mixing regime. It preserves enough structure and allows for sparsity, so not everything has to talk to everything else, but it avoids that immediate collapse. It's just a beautiful piece of engineering meeting the physical demands of the system.
So what this all really means for you, the learner, is pretty profound. The transformer, at its very core, is a system that is physically driven to collapse on itself to reach a state of total synchronization.
Right.
And every single major architectural innovation we've seen, layer normalization, the huge shift from post-LN to pre-LN, this clever logarithmic scaling, it's all been successful because it acts as a kind of elegant mathematical brake. It's all about managing, stabilizing, and slowing down this constant physical drive toward consensus.
And it's important to remember, the analysis we've covered has been mostly deterministic. It's what should happen in a perfect, noiseless world.
But the real world has noise.
The real world has noise. And so the next frontier is what's being called noisy transformers. We model them with stochastic differential equations. You have to account for noise from, finite precision in the computer or just randomness in the data itself.
And while a simple version, the noisy Kuramoto model, is pretty well understood,
Yeah.
the full noisy transformer is what? Still a mystery.
It's a wide open landscape. We still don't have a good quantitative description of those metastable states. Do they even exist in the same way? How long do they last when you're constantly injecting randomness into the system?
The core question is still out there.
It is. How stable is this whole beautiful managed structure, really? What are the absolute limits of stabilization when noise is always trying to knock it down?
A deep question indeed. The physics of AI are still being written. That's a wrap for us on this deep dive.